Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about making oxygen on Mars. So let's dive right into it. Well, first a cursory glance over oxygen itself. Well, it is very important for humans. I'm reasonably sure I don't have to explain that to you guys. However, you also have to understand this aspect that oxygen is the other half of rocket equation, aka no matter which cycle you use, you generally carry your own liquid oxygen. So let's say you want to use methane of SpaceX, again you're gonna need liquid oxygen. You want to use hydrogen of some other design, you still gonna need oxygen, or something else, you still will need oxygen. Oxygen is an absolute requirement. While a human may consume, let's say, 2-3 kilogram oxygen per day, a rocket will consume few tons to sometimes few hundreds of tons in few minutes. So this is a very serious requirement. So flat out transporting it from Earth to Mars, it's just flat out unviable. Flat out, like no, just nope. It cannot be done tangibly. So Mars has one resource that we utilize to solve our problems, that is carbon dioxide. Now Mars atmosphere is 95% carbon dioxide. That means flat out, if you just have a raw air compressor running, you're gonna get 95% pure carbon dioxide, which is very good because many things can handle that kind of impurity levels. However, this is one very critical aspect. The pressure on basically Mars is almost zero, aka it's almost 0.088 psi. That's the average. Some places have a bit more, some places have a bit less. And the place where rover itself supposed to be landing, that place is targeted around 7 millibars, aka around zero point 0.1. But they are gonna land it in a crater, so psi there is bit higher. Now what the hell is gonna do with basically carbon dioxide? Now we do know how the heck plants break basically carbon dioxide. However, what they do is, in simplest term, they take carbon dioxide, they take water, and they basically remove oxygen. They take the carbon and take the hydrogen from water and then make hydrocarbon. That is the founding building block of tree itself. Now again, we do not have the luxury of carrying water there, so we have to do it with itself, like, okay, carbon dioxide, that's it. So what can we do? Now what we are doing is basically taking one molecule of carbon dioxide and putting electrical potential into it, which is giving us carbon monoxide plus one unstable oxygen ion. So to balance the equation, or to make sure that we actually have different outputs rather than just like some active ions, if you have two carbon dioxide, then you're gonna get two carbon monoxide and one stable oxygen, because oxygen has to be diatomic, aka O2. We need something like that to be, in order for it to be stable. So how the heck we are achieving this magic without introducing water or sunlight or things of that nature? Well, what we are utilizing is classified as solid oxide electrolysis stack, aka it's a fuel cell in reverse. Now what fuel cells generally do is they take basically fuels, be it oxygen, be it hydrogen. They take some sort of chemical energy and convert into electrical potential. Now we are doing it invert. We are taking electrical potential and creating chemical output, and this has to be done at 800 degrees Celsius. Now that aspect is very crucial because carbon dioxide is a burnt byproduct, aka if you burn something, you get carbon dioxide. It's like water. You burn hydrogen, you get water. You burn carbon, you get carbon dioxide. It's a stable form. So you have to have the heat of 800 degrees Celsius to even start to destabilize it. And at that point, it's like, okay, it is like, in a scenario where it's like it might react, it might become unstable, but it's still intact. So in this stack, this basically fuel cell, quote unquote, what we're gonna have is we're gonna have some what we classify as catalyst. These catalysts is gonna pull on basically oxygen part of the carbon dioxide, and then we're gonna run electricity through it. All those things combined, basically heat, electrical potential, and catalyst, these three things combined is gonna give us that option of, okay, liberating oxygen, complete oxygen, aka O2 from carbon dioxide. That's the reality. That's all it's happening here. That is why it's hot, and that is why you see the NASA's photograph and it's in oxygen, basically gold box. Gold is there to properly insulate it. So that's how we're gonna create oxygen from Mars without needing water. Now, another aspect happens is that you make a fuel stack. Fuel stack cannot run on vacuum. It needs some level of pressure. Again, it does not need 15 psi of Earth's atmosphere or something like that, but at least it needs some pressure. It will simply not work without pressure. So Mars atmosphere is almost vacuum. Flat out, it's very close to vacuum. So we need carbon dioxide to be compressed, and I mean thoroughly compressed. So this time NASA is using scroll compressor. Now these compressors are rarely used for large scale application, and even NASA is not aiming for this to be upscaled built for manned mission. This was like the smallest they can build for the volume and power requirements, and it was like it's more based on as a technical demonstration rather than like, okay, this is what we're gonna upscale when we want to bigger. So do not focus on too much like they are using scroll compressor. That is like, stopgap solution. So their intake, where they want to land, the expected outdoor temperature, I'm saying outdoor pressure is 0.1 psi, and they're gonna land inside a crater, so they're supposed to have a bit more psi, and this compressor is gonna make it into 1 psi continuously. That is critical aspect. There is no reserve cylinder, there is no valve. They could not do that simply because of the size limitation. So they have continuous running. Basically, this compressor will run only then the fuel stack will be activated. It won't be like compressor will keep running until it pressurizes a tank, then that tank will feed into the fuel stack. That will not be done. It will be direct feed. So this is a pressure aspect. Now, so far everything sounds good. You take a basically Martian atmosphere, you compress it, you send it through a fuel stack, and voila, your oxygen. Now, everything about this is absolutely true. It can be done. Physics is there, engineering is there, and we soon gonna test it. However, the only core component, the only thing missing, it requires energy, because you have to understand, we are not reacting something that is like, ready to react. We are reacting something that is already reactive. It's in low state. We have to make it into high state. We have to make it quote unquote unstable. So power requirement is insane. Now this whole setup, NASA's target is around a 2 kilogram oxygen production per hour, and that is just not only for human colonies, for like everything. That is like the bare minimum. If we send something that generates oxygen, this target must be met around 2 kilogram per hour. That is for like making liquid oxygen for rocket and oxygen for breathing and other experiments and all that jazz. So air filter is also a critical aspect, because Mars is very dusty. Not only that, the dust is kind of clingy. Basically, it's statically charged, so it clings to things and clings very hard. So this is also another aspect. And anybody of you who have worked with filters and all that jazz, they know filter restricts airflow, aka it increases your power consumption for the fan or compressor, whatever have you. So that itself becomes a headache, because okay, now you have, especially if you want to extract 2 kilograms oxygen per hour, you're gonna need very big airflow. Then you're gonna need even bigger air filters. Those itself will become a power draw, because you're going to need to clean the filter out. Then air compressor. Now air compressor, you are talking about like best case scenario is 0.1 psi. That's the best you can get on Mars. Again, you're going to design something that can handle in worst case scenario, so that will be like 0.08 psi. So again, your compressor has to be strong. Now NASA's targeting is around what we classify as axial compressor, aka more like a jet turbine. That's their big scale one, and they're going to have like 3-stage axial and some other types of compressor to get that flow, steady state flow. That itself is a very big power draw. It's bigger power draw than the what you're gonna energy loss you're gonna have through the filters. And then we come to solid oxide electrolysis. This is the biggest power draw. Like this would be like 80 to 90% of your power consumption. Now, to achieve the target goal of NASA's around 2 kilogram per hour, they came up with best case scenario. This is the best case. We have not tested it on Mars. That's why MOXIE is being created. Their mathematical assumption is around 14 kilowatt minimum. Let that sink in. 14 kilowatt of power continuously to create 2 kilogram per hour, and you have to do it continuously, otherwise you will simply not have enough oxygen for the rocket ship. So this is the whole reality, and the crude awakening of that is solar power is not enough. And NASA learned this the hard way, and you can have easily seen it, like their rovers went from solar power to be like, yep, we can't deal with this solar energy, we have to utilize nuclear power. And NASA has been in parallel developing something known as NASA's kilopower reactor. Now this reactor is a nuclear system, and it works on sodium rather than water, so there is no boom explosion happening here. And you must have seen almost all NASA's presentation have this kind of umbrella looking structures. Now the reality is, these are the only thing that comes even close to running this kind of power draw, and this is just for the oxygen half. And if Elon Musk wants to run, let's say, methane circuit will be even more expensive than energy wise, more expensive than this one. So you're gonna need very lot of them, these nuclear power plants, or really huge solar farms. On top of which, solar farm will not work that well, because not only you are adding mass to your rocket ship which has to carry the solar farm, but there is not enough solar flux. Flat out, on top of that, it will not work half of the time, because again, night. And another aspect is that there are dust storms that last for around months, so solar farm is not doable. Now again, NASA still wants to have solar farm as a primary boost backup. Every critical system will be run on nuclear as a backup system. Like no matter what happens, the main scenario is keep working, because you only have 2 years. You only have 2 years to basically refuel your rocket ship, because if you miss that window, you have to wait another 2 years. So flat out, those things will be powered by the nuclear setup, and solar will be like for extra things like lightning, greenhouse, and all that jazz. So power requirement is a very crucial thing, and that is why like anybody who's expecting like we can just go to Mars on solar power, it's like yeah, no, flat out. No, we have to have nuclear power, and that is why like you can easily see every NASA's presentation is like we have kilo power reactor, and that is why this is being speed developed very critically alongside with everything else. Because again, let's say we made the fuels, like let's say we made everything, still gonna consume power, because to extract basically oxygen out of oxygen out of carbon dioxide, you not only have to create electrical potential, you also have to create high temperature. 800 degrees Celsius is not something like oh, normal heater or your mobile phone can heat that much. It's very high power draw. So that is the biggest hurdle so far, and that's just for the oxygen. I'm not even going to plan for basically carbon dioxide. So what we can expect in the future, now this is the most important aspect of 2020 rover. This box is already being integrated with the rover. Now rover is, think of this way, the 2020 rover is basically exact model of Curiosity rover. However, we learned a lot of things from Curiosity rover, mainly being that NASA, basically Mars surface is very brutal. It destroys wheels like there is no tomorrow. So this time the biggest difference you're going to notice, the wheels are like tank wheels. They learned this the hard way, that the wheels have to be ludicrously strong to handle it. Now this is what we call first suite in-situ utilization, and if you want exact pin precise detail, I have provided a NASA's PDF down below, you can check that out. Now this technology must work. This is not an optional technology, this is a must-have technology in order to have a human colony. Flat out, if this technology fails, NASA will keep doing it until this succeed. Otherwise, flat out, there will not be a manned mission. It has to work. It's not a luxury, it has to work, because NASA's designs include a hydrogen based rocket engine, because hydrogen is so light, you can carry insane amount of hydrogen. And basically hydrogen is if you have around, let's say, in 10% of your weight can be hydrogen, and 90% could be oxygen if you want to make a rocket out of it. So that luxury is there if you can create oxygen on the spot. That is why oxygen is the first thing they are targeting. Once this works, and let's say SpaceX starships actually comes becoming closing and actually starts working, then they will send another batch which will figure out how to create methane. So this is the reality of it. Basically it must work in every scenario, in every basically day, night, everything. They will test it out, and because of the power draw, the nuclear power plant that this puppy has, it's again, it's isotopic thermal generator. It does not have too much power, but so that power comes to the batteries charges up. Once the battery is fully charged, then the project basically all the experiments labs have trigger one by one. So this will be started sometimes earlier during daytime, sometimes during nighttime, sometimes during different season. Basically, this is gonna be operating in the burst mode, and their target output is around a few grams of oxygen per hour. Basically, to keep a small dog alive, it could be done. If you want to keep a small dog alive, it can be done with this. To make a human alive, you're gonna need a much bigger, basically power plant. So that's the reality. It's like it's gonna operate in small bursts, because again, it's gonna drain the battery to almost zero every time this works. So this is the future aspect of it. Everything relies on this puppy to work. If this works, human can go to Mars. If this does not work, we're gonna send another one to make sure this actually works. So it is very, very what we classify as linchpin technology. This must work. Now, this was my presentation on NASA's golden box, basically making oxygen in Mars. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.